All right, so we've just spent a lot of time looking at integration, theoretically. So now, of course, one of the main applications is volumes. So we're going to have a look at some techniques. Now, all we've really seen at this stage is the two-unit idea. Difference in four-unit is we build it up. So let's, first idea is slicing the shape, or the solid, perpendicular to the rotation. And this is what we're actually used to. So if I wanted to go around the x-axis, for instance, so let's draw in a random curve, y equals some function of x, and let's say, just like in two-unit, we'd say, okay, if I want to rotate this curve between A and B, and we're going to go round the x-axis. Difference is, what we look at here is each of the individual slices. If you cast your mind back to when we started looking at integration and finding areas under the curves, what we basically said was, we're going to break it up into infinitely thin rectangles, and we know how to find the area of a rectangle, and then we summed all the rectangles up and found out, oh, what do you know? That's the primitive function. I can integrate and get the area. It's exactly the same idea. So I'm still going to get this infinitely thin rectangle, and I'm going to rotate it round the x-axis, but I'm going to do that for all of those rectangles. Now, each one of those rectangles creates a, some sort of disk, which has a thickness of whatever the change in the x value is. But of course, we could find the volume of that disk. The radius would be the y value. But of course, I need it in terms of the thickness. The thickness is in terms of x. So that's all right. We know the equation of the curves y equals function x. So I can say, all right, the radius is whatever that function happens to be. So I know the area of the cross-section there would be pi times the radius squared. And that's where we get our formula that we use in two-unit. So if I wanted to look at the change in the volume then, it would be the surface, that cross-section area, times by the thickness. In other words, volume of a cylinder. So times delta x. But I want to sum up all of these cylinders, going from an x value of A to an x value of B. And I'm summing from A to B. And just like we saw with area, we say, oh, hang on, this turns out to be primitive function. So this sum, when I sum them all up and approach 0 for the thickness, I get the integral. Now, pi, of course, is a constant, so I can bring that to the front. And what we saw in two-unit, we didn't say function x squared, we said y squared dx. So here's the difference, I guess, between four-unit and two-unit. In that, in two-unit, they would just quote volume equals pi times the integral of y squared dx. Whereas in four-unit, we actually build the integral. And it seems like a lot of extra work when we know that formula. But of course, this is just one specific case. We can now generate this idea to other solids as well, which we'll do throughout the course of this particular topic. So if it was around the y-axis, I'd do exactly the same sort of thing. There's my random curve, y equals some function of x. And I'm going to take the slice perpendicular to the axis of rotation. So this time it's a horizontal slice because I'm going around the y-axis. So the slice is perpendicular to the axis. The thickness now would be the change in the y value. So if I had that x, well, the radius would be the x value, but that's no good. I want the y coordinate. I've got a function up here. Of course, that's y equals. I want it as x equals. So I can use my inverse functions and find out, well, x is some other function of y, whatever it turns out to be. So area y, basically we get exactly the same thing, but now it's in terms of y instead of in terms of x. And so my overall volume will be that area times the thickness. And so if I was to find the total volume, I'll sum all of those solids up, and that becomes an integral. And of course, I'm using the y values. Notice C to D on the y value there. Okay, well, let's do it via means of an example. The actual questions themselves, the early sort of ones, are not that hard, the integration. I guess it's the setting them up becomes where the marks are worth. So if you just go straight to the two-unit formula, you're not going to get many marks, because obviously a two-unit student can do that. It's not what they're interested in a four-unit paper. So let's draw a picture. It's an upside down parabola. So I know, yep, x-intercept's minus 2 to 2, y-intercept to 4. I'm going to go around the x-axis. So I want my slice perpendicular to the rotation. So therefore I want a vertical slice. So everything's going to be in terms of x because the thickness is the change in the x value. Now if I was to rotate that, I get my solid, my disc, and the radius would be the y value, but in this case I know in terms of x, the y value is 4 minus x squared. So the cross-sectional face will have an area of pi 4 minus x squared squared. So therefore the volume, or the change in the volume, will be pi, and I've just expanded that out, times the change in x. So to find the overall volume, I want to sum up all of those cylinders. So from minus 2 to 2. Now, you're looking at it again and thinking, oh, can I leave these steps out? And the answer is no, because what we're interested in here is to see if you know where it comes from. The actual final answer probably isn't that important in the scheme of things for this. So it is important you show your element of a volume, so delta V, and where you've got it from, how you've created it, and then you say, okay, well now my volume will be the sum of all these things, and then from there we can say, okay, well that'll be 2 pi times the integral. Notice I've used the symmetry of the shape there, so now I'm going from 0 to 2, but I've got 2 pi out the front. We can still use those techniques. And like I say, the actual integration itself is not that hard, it's just a polynomial. So add 1 to the power over the power, sub in 2, and unless I make a silly mistake, I'll come up with the actual answer. So hopefully you can see why the actual marks for the answer, well, it's not really, that from this step, 2 pi the integral to here really is a 2-unit question. Here's the work, setting up the disk, showing, hey, this is my volume, this is where I get it from. Let's have a look at another one. But the idea of using this is I'm no longer restricted to rotating things around the x-axis and the y-axis. Same curve, but I'm now going to rotate it around the line y equals 3. So let's draw the same curve in. But now I'm going to rotate it around y equals 3. So I'll need to find those points of intersection so I know the x values I'm going from. And it turns out to be minus 1 and 1 are the x values. I'm rotating around. So my slice will not go all the way to the x-axis. It'll stop at the axis of rotation, which is y equals 3. So if I was to rotate that, I'm still going to get a disc or a cylinder, if you like. But the radius will no longer be the y value. It'll be y minus 3, because I'm stopping at the line y equals 3. Well, I know the function for y is 4 minus x squared, so therefore the radius for this one is 1 minus x squared. So I'll subtract 3. Other than that, it's now the same. Okay, well, what's the area of my cross-section? Pi times the radius squared. So therefore my volume element, my delta V, will be that times delta x. I need to sum all of them, but not going from like the last one where it was minus 2 to 2. Now going from minus 1 to 1. And now the integration again, it just becomes like a 2-unit question from that point on, where we add 1 to the power over the power. And there's our answer, 16 pi on 15. So we actually could end up with a lot more interesting shapes. You'll notice I said discs and washers. Because what happens if the slice is an area between 2 curves? So let's have a look at that. I've got y equals x squared, which of course is our standard parabola, and x equals y squared, which is a parabola on its side. And we're going to rotate it around the y-axis. So let's draw in the slice. If it's around the y, oh yes, find the point of intersection is going to come in handy. So 1. That slice will be horizontal because I'm going around the y-axis and I'm doing it perpendicular to the rotation here. So if I was to rotate that around, I'd get like a washer. You know, like when you're putting bolts in, you have the washer in there. So we've got like a washer there. So what I need to do is find the area of this cross-section, or this, there we go. I'll need to know the outer radius, but it'll be in terms of y, because my thickness is in terms of y. So the radius, yes, that is the x value, but it's y to the power of a half. the inside radius, which is my blue curve, it's x equals y squared. And so the actual area of that cross-section would be pi times the big radius squared minus the little radius squared. And I come up with a new function for volume, delta V, pi times y minus y to the 4 delta y. And so I'm going from, well, 0 to 1. 0 to 1. We're just going that small little section in between the two curves. So let's integrate that, add 1 to the power over the power, and we come up with our answer. Now what we've got to be careful with is sometimes the boundaries might change, and in that case I might have to do two separate volumes and add them together. Always got to have a look at, are my boundaries consistent? Am I always going from the curve to the axis or the curve to the other curve, and change accordingly? This is quite an old question now, but 1996, this region, so we're given this picture and we're going to rotate actually around x equals 4, not the axis there. Curve x plus y squared equals 0. Might have been a bit mean writing it that way, because what it basically is a standard parabola. You just don't recognise it when it's written that way, but if you think about it, that is x equals minus y squared. So it's a parabola on its side, going the other way. Also bounded by x equals 1, y equals 1, y equals minus 1. That particular shape, we're going to rotate around 4. And what we'll end up with is, you know those thumbtacks, those coloured ones that you can sometimes press in? And how that's sort of that sort of shape when you rotate around? So let's find its volume. It helped us because it said, well, show the area of the annulus at height y. Let me just go back to that picture. And so they drew the slice in for us so we could see where the slice was. So the annulus is that technical name for the washer, or the cross-sectional face. And so if we rotate that around 4, so okay, I'm going to get this sort of washer shape. The thickness is delta y. The outside radius, the inside radius, first of all, I've worked out. And I'm going to need the outside, which I call capital R, so I can distinguish between the two. Now I've got to be careful here, working it out. What is the inside radius and the outside radius? So the inside radius is going from x equals 4 to x equals 1. It's just going to be a consistent, every slice, that inside radius is just going to be 3. And so we don't have a problem there. So the outside radius, however, will be going from 4 to the parabola. Is that enough? No. So it's going to be 4 minus the x value here. Now, you'll notice it says 4 plus y squared, and I've said it's minus. Well, that's because the shape I've got, you'll note, is going to have a negative x value. So when you go minus the x value, it becomes a bigger number. So it's always going to be from the centre minus the x value, which in this case turns out to be plus y squared. Okay, so let's work it out then. So capital R was 4 plus y squared. Little r was just simply 3. So pi, 4 plus y squared squared minus 3 squared. And sure enough, that turns out to what they were looking for. Now, I guess the advantage of that question that year was if you couldn't quite get that, you might have mucked up that and had plus x instead of minus x. At least you had the expression you could keep going with. Hence, now go and find the volume. All right, well, I've got to sum up all of those. So the volume then, my delta volume, will be that area times the thickness y. So I'll be going from, and it's y values I'm working from, so it was minus 1 up to 1. And it now becomes a very simple integral to do. So add 1 to the power over the power, and there's our final answer. Okay. All right. So there's several questions there. Our Cambridge exercise 6A. Patel, I've taken some out of 3A, some out of 3B. But I'll warn you, some of the ones I've picked, I might have picked the wrong method. And what I mean by that is they were probably intending us to do it the method we'll look at tomorrow, and it would be a lot easier, but I just felt mean and thought, this will make a nice little challenge, let's do it the wrong way. Okay, so there's stacks of questions there. You might want to leave some of them for later for revision and just do the Cambridge ones now. Up to you how you want to organise that one.